All right, back again, part 3 of this exciting series of videos about electrocardiography. And this time, we're going to talk for a few minutes about simulation. This is, again, another one of these big domains. I'll try not to get too off track. We talked before about the way to think about electrocardiography as being the integration of a source, a bioelectric source. We talked about the dipoles a lot. There are other source models. A volume conductor, that's the torso itself, the thorax that sits between the source and the body surface where we do our measurements. And that's the scenario that we think about conceptually for the theory. We think about it when we're measuring and how to interpret those measurements. And of course, that's what we have to replicate when we go to simulate this same situation. And of course, we have a lot of simulation tools and a lot of research in this domain over, again, a number, probably 40, 50 years. Certainly the breakthrough time was probably in the 70s when we finally had the computers and the underlying methods to make this happen. Now, there's a technique that we now call in the genre electrocardiographic imaging. So this is ultimately meant to become an imaging modality in which the imaging is not of anatomy, it's of function. So it's electrical functional imaging that we're doing here. The input to this are the body surface electrodes. Again, body surface potential mapping, style recording, where we have a complete picture of the electricity on the thorax. Then we feed that through some simulation software that implements some numerical methods, which are driven by physics-based mathematical equations. And then we solve a whole bunch of other problems along the way, and we ultimately recreate or reconstruct those sources non-invasively from measurements we make in the body surface. That's the name of the game here. This image captures that process, again, not quite schematically because the images on the left are actually recorded images. So they're showing us, in this case, a slightly different source model. We don't need to get into those details, but that's the heart, anterior, posterior, actually the outside, the inside, all rendered nicely. That goes through this geometric model. That's the volume conductor. And when it goes from left to right, that is what's called a forward problem where we know the source and we want to predict the electrocardiogram from that. That's fun mathematically, but not so useful clinically. Clinically, again, we're trying to reconstruct, so we're trying to go from the right to the left. And that is, in the mathematical language, that is what's called an inverse problem. That's trying to reconstructing something that's far away that we've measured remote signs of. Inverse problems arise across many different disciplines. It's a very broad field of research and practice and engineering. Every time we create an MRI image or a CT image, we're really reconstructing and we're solving a different type of inverse problem. Seismic data, the reflections of acoustic sound that we penetrate, we send down to the earth and bounces back to recreate layers of underground mineral resources. That's all reconstructed using the same numerical framework of what are called inverse problems. So again, big domain, we're just tapping into it for our particular purposes. The tool that we're going to use now for a homework assignment is actually going to implement this forward solution. So here we're going to be able to interactively control the heart, adjust features in the heart, the timing of the action potentials, the size, duration of the action potentials, and then visualize immediately the resulting ECGs and the resulting body surface potential maps. And this is a tool that has again been around for a while now. It's in its third or fourth or whatever version. It's highly used as an educational tool, used by clinicians to try and interpret ECGs. It's really a wonderful tool. And again, we'll have a homework based on that. We also here at the University of Utah and the Scientific Computing and Imaging Institute have created toolkits to do this same thing. Ours are not quite so agile and user-friendly perhaps as this other software I described, but we also carry out this kind of research. And if you have questions, please ask, but that's really all I have time to say here. But ECG Sim is this piece of software that we'll use for our simulations. And again, the idea is that we have a source model that's built into the software, but we can adjust the parameters of it. We can adjust the underlying features of that source model. It's inside its own volume conductor. There's a geometric model built into the software. And then it produces the associated electrocardiograms and body surface potential maps. And we can use that tool to explore different settings, different situations, much like you did with the modeling of the membranes, where you adjusted parameters of the action potential. Here we're going to adjust parameters of the bioelectric source model, the dipole, or the wavefront, or whichever model that you want to play with. And there are different models in this particular software. And then finally, as I mentioned, this electrocardiographic imaging, this is a commercial tool. It is used in clinical practice. There are 2 or 3 companies that make this, so it's not just pie in the sky. It's in its early time for sure. It's extravagant clinically and technically. These are not inexpensive systems. They're still fine for the patients because whether you're wearing 5 electrodes or 500 doesn't change dramatically the burden on the patient. So it's a very attractive option from that regard. But there are many technical hurdles in the way of making it a fully robust, dependable way of capturing electrical activity. And that's where the research really is. Research in the academic world and research in industry. But this ECGI systems exist. Here you see a schematic. Again, from this same group I mentioned before, directed by Yoram Rudy, now the company run by some of his former students, in which the process starts with imaging to create a geometric model. Then we record the electrical information from the body surface using all these electrodes. And then we do some magic numerical methods and reconstruct the electrical activity. That's, in a nutshell, the process. And again, it's real world. It actually exists. For our purposes, it's just probably enough to know these basic steps. We have a source model that generates electricity of some sort. We have a volume conductor in which it sits. We have measurements we make. And we can actually tie those all together in a mathematical model, in a numerical framework, and actually do simulations to replicate that. And that's very typical of a lot of the modern world of physiology. It's quantitative, it involves modeling, it involves complex measurements. This is just one example of that. So we'll see a little bit of this in the lab coming up, and then with the data we have for you to play with. I hope that was interesting, motivating, clarified a few things, and again, got you prepared to jump into the lab and the homework where we start to explore these things in a little more detail. Thanks for your attention again, and we'll see you soon.